From high above the South American desert, these neon-colored pools look like abstract art. But those colors are the byproduct of a massive ecological trade-off. Global lithium consumption is rising by nearly 9% every year. Most of that demand comes from a single source, the batteries powering our electric vehicles. This map outlines the borders of Chile, Argentina, and Bolivia, a region known as the Lithium Triangle. Of the estimated 115 million tons of global lithium resources, over half is concentrated in these salt flats. This lithium exists as a liquid brine trapped in subterranean aquifers, buried beneath some of the most arid landscapes on the planet. To extract a single ton of lithium, mining companies must pump and evaporate roughly 500,000 gallons of water. It is an industrial process called water mining. Every electric vehicle battery produced through this method accelerates the depletion of water in the world's most fragile ecosystems. Deep wells in Argentina pump brine from aquifers 400 meters below ground. On the surface, the desert sun evaporates it over 18 months, yielding a lithium concentrate. This cheap method is inefficient. Up to 70% is lost or trapped. Australia takes a faster approach. They mine a hard rock mineral called spodumene, which can be processed into lithium much more quickly than using evaporation ponds. Hard rock mining requires calcination, heating the minerals in massive industrial kilns. This high-temperature step generates a carbon footprint far larger than any brine operation. Subscribe to the channel if you want to understand the hidden supply chains that power our daily lives. Engineering the green transition forces a difficult choice. We must either generate massive carbon emissions through hard rock mining or accept massive water destruction from brine extraction. Nowhere is this choice more evident than in Chile's Salar de Atacama, an ancient and highly specialized environment. Lithium operations have already consumed 65. It acts like a selective chemical filter that traps lithium ions while allowing the water and other minerals to flow through. This method reduces processing time from 18 months to mere hours and boosts recovery rates to 90%. But DLE is energy-intensive and requires significant capital. Most importantly, it uses massive amounts of fresh water to wash the captured lithium from the chemical extractants. The technology also must be custom-engineered for every salt flat to handle specific impurities like calcium or sulfate, preventing it from being a universal fix. While DLE can speed up the supply chain, the underlying resource drain remains a major engineering hurdle. There is currently no way to mine the materials needed for a high-tech future without an environmental cost. Long-term sustainability requires a move towards circular economies and aggressive battery recycling protocols to reuse the minerals we have already extracted. Think of the Atacama the next time you use a battery-powered device. Reaching a zero-emission future depends on our ability to look past the battery and solve the crisis happening at the wellhead.